All right, so I'm recording, and now I'm going to share my document camera. All right, this is my reminder to record. And here's problem set number 11. So as I mentioned before, this is a challenging problem set, probably the most challenging in the course, I would probably say. It's also the most realistic, though. This is probably the most realistic thing that we've done so far in the course, because this is really looking at a fairly realistic situation where you're heating up a liquid inside of a boiler, and you got some layers of insulation around that boiler, and it's inside of a room, and you don't want to lose too much heat from the boiler, because that's just inefficiency. You want to run a steam pipe from that boiler over to the turbine, and you don't want to lose thermal energy from the boiler or from the steam pipe. So this is a fairly realistic situation of calculating how much heat are you losing from this boiler due to the various modes of heat transfer that we've talked about. All right, so we went over this briefly at the end of the video on Monday. We've got a boiler inside here, and we're given all the dimensions of the boiler. It tells us it's a 3 meter in diameter, and it tells us the steel boiler walls are 4 centimeters thick, and the insulation is 10 centimeters thick. And then it tells us the dimensions of the room. The room is 15 meters long by 15 meters wide, and the walls are 5 meters tall. The boiler itself is 3 meters tall, and we're going to ignore heat transfer from the top and the bottom of the boiler and the ceiling and the floor of the room. And we're given that the temperature of the bulk temperature of the fluid inside here is 300 degrees Celsius. So it's probably at a pretty high pressure in order to be a liquid at 300 degrees Celsius. Got to be at a real high pressure. And the air and the room walls are 30 degrees Celsius. We've got air flowing around the boiler due to ventilation that's 0.5 meter per second. And we want to calculate the total rate of heat transfer from the bulk fluid to the air in the walls. So what's the heat loss from inside the boiler? So here's all of our parameters that we're going to need. And the first step for most of these problems, well, after you understand the problem and gather the parameters that you need, is to draw the thermal resistance network. So I think I drew this at the end of the video on Monday to help you out, to give you a head start on this problem. So if you think about what's the thermal resistance network going to look like, here's T1, here's the bulk fluid temperature inside here that's at 300 degrees Celsius. And then any heat that is going to escape first is going to have to go through the convection layer between the bulk fluid and the interior surface of the steel. So that's actually a layer of convection. And it actually, I believe, tells us, it tells us what that convection coefficient is. So that's the thermal convection coefficient. So that's going to be pretty easy to calculate that. Then any heat has to go through the steel layer, and it doesn't have a choice. It has to go through the steel layer and then the insulation layer. So these are going to be in series. The steel layer, that's conduction, and the insulation layer, that's also conduction. And then it gets to the outside surface of the boiler. So it's right here. And then you can have heat transfer via convection from the surface to the air, the moving air, or actually, you can have heat transfer from the surface via radiation to the walls of the room. So because it has a choice here, the heat can either transfer via convection to the air, or it can transfer via radiation to the walls. Because it has a choice, they're in parallel. So you have this convection resistance and this radiation resistance in parallel. But the convenient thing is that the air is at the same temperature as the walls. So both of them are going to T2. And T2 is given as 30 degrees Celsius. So this is the problem. T1's at 300 degrees Celsius. T2's at 30 degrees Celsius. We have a bunch of resistances in series and in parallel. We want to know what's the heat transfer rate. All right. We can look ahead just a little bit and we can say, how are we going to calculate this? Well, convection resistance is 1 over HA. And we're actually given H, and we can calculate the surface area inside the boiler. So that's going to be pretty easy. Then we've got this resistance. It's conduction. It's through a cylinder, so you got to use the equation with the natural logs in it. But all those dimensions are given, and the conductivity is given. So that's pretty easy also. Same with this one. Oh, sorry, you couldn't see that. Same with this resistance. This is going to be pretty easy also because we got all the dimensions. We got the conductivity. It's going to be pretty easy to calculate this. So these three, pretty quick and easy. This one is going to be a little bit more challenging. It's convection, but we're not given the convection heat transfer coefficient H for this resistance right here. We are given the velocity of the air. So we're going to have to calculate the Reynolds number for this situation. Then we're going to have to calculate the Nusselt number. Then we're going to have to use the Nusselt number to get the convection heat transfer coefficient. And then once we get that convection heat transfer coefficient, then we can calculate the resistance as 1 over HA. So that's going to take a little bit more work. It'll take 4 steps or so. But we have all the information to calculate that. So we can do that. It's not too bad. This one is going to be the pain in the butt because the problem with this one is that our rad total depends on the delta T between here, and we don't know this temperature. So this is the one that's going to be a pain in the rear end, and we're going to have to do some basically guess and check. I mean, it's an iterative. The nice way of saying guess and check is iterative. So we're going to iterate our solution 3 times and see if we can figure out what this temperature is, which would tell us or allow us to calculate the total resistance accurately and then calculate the heat transfer rate for the whole thing. So that's the overview. That's what we're going to do. So here is our thermal resistance network. The first things we're going to do is calculate that and that and that. All of those are pretty easy. So here's the convection term inside the boiler. 1 over HA is the thermal resistance. H is given in the problem, 50 watts per meter squared per degree Celsius. The area, you got to calculate that. That's the inside surface area of the boiler. So you got to take pi times the diameter times the length inside the boiler. So it's pi times 3 meters times 3 meters. And your thermal resistance for convection right here turns out to be 0.0007 degrees Celsius per watt. So that's that one. I already got that one. Next one is this conduction term. This is also pretty straightforward, pretty easy. We know our thermal resistance equation for conduction through a cylinder. It's the natural log of R2 divided by R1 divided by 2 pi Lk. So we got to take the outside radius of the steel, and we're told that the steel is 4 centimeters thick. So the outside radius is 1.54 meters. Inside radius is 1.50 meters. So you take the natural log of that and divide by 2 pi times L, that's the length, in this case the height, it's the height of the cylinder, times the conductivity of the steel, that's given. So the units cancel out and you get a value of 0.00002. It's a pretty low resistance, degrees Celsius per watt. So that's that one. Next is this one. This is going to be pretty easy as well, very similar to that one. So we've got our R3, that's outside the insulation, and we're told the insulation is 10 centimeters thick. So R3, in this case, the outside radius is 1.64 meters. The inside radius is 1.54 meters. Take the natural log of that. Divide by 2 pi Lk. L is still the height of the boiler, and here's K for the insulation. So our thermal resistance for conduction through the insulation is 0.1113 degrees Celsius per watt. So just take a look here. Notice the resistance through the insulation is much higher than the resistance through the steel or the convection from the fluid to the inside wall of the boiler. And that kind of makes sense. I mean, that's why you put insulation on this thing, right? To give you a large thermal resistance. So it makes sense that it's a much larger value here than here and here. Next, we got to get this one. That's the convection from outside the boiler to the air. It's a little bit more involved because we have to calculate some of these things. We're not just given H like we were for this convection term. So it's not that bad though. You got to start with your Reynolds number. You take the velocity, which was given to us, times the characteristic length, and that's always the diameter when you have flow around the outside of a cylinder. So the total outside diameter, including the steel and insulation, is 3.28 meters. And you divide by the kinematic viscosity, which was given, 2.306 times 10 to the minus fifth meter squared per second. And the units all cancel out, and you get a Reynolds number of 71,000 something. We're given the Prandtl number. You don't have to look that up. It's 0.7111. And now you got to look in your table, back a few pages in your lab manual. You're given a table for flow over a cylinder for Reynolds number in the range of 40,000 to 400,000. You're given this equation in your lab manual a few pages prior. So you plug in numbers for the Reynolds number that we just got, 71,118. It's okay if you have a little bit of rounding error, that's fine. Won't affect the result that much. And our Prandtl number, plug that in, and we've got these exponents to the 0.805 for the Reynolds number and to the 1/3 for the Prandtl number. So you get a Reynolds number of 194.0. So now you know the, excuse me, that's the Nusselt number. I think I just said Reynolds number. We're finding the Nusselt number here. So that's the Nusselt number, 194.0. Now we can use the definition of the Nusselt number. It is H times LC divided by K. We know all of this except H, and we're trying to find that. So rearrange for H. It's equal to the Nusselt number that we just calculated, 194, times the characteristic length, or sorry, excuse me, it's times the conductivity. So the conductivity is given, and it is for the air, it's 0.03095 watts per meter per Kelvin. And then we divide by the characteristic length, and that is 3.28 meters. So we plug those in, and we get 1.83 watts per meter squared per Kelvin. So now we got H. Now we can find this resistance because it's 1 over HA. So 1 over HA, there's our H that we just calculated. Here's the area at the outside of the boiler. So it's pi times the diameter, 3.28 meters, times the height of the boiler, which is 3 meters. So finally, here is our thermal resistance for convection. It's 0.0177 Kelvin per watt. And we can use the same thing in degrees Celsius per watt because the delta T of 1 Kelvin is the same as a delta of 1 degree Celsius. So we can use that as 0.0177 degrees Celsius per watt.
Dr. Ullman, real quick, for the Reynolds number, what was your LC value that you used?
So you're talking right here when calculating the Reynolds number. So it's always going to be the diameter of whatever cylinder you're looking at. So it's going to be the outside diameter because we have flow around the outside of the cylinder. So the outside diameter is 3 meters plus 4 centimeters plus 4 centimeters, because that's the thickness of the steel wall on both sides, plus 10 centimeters plus 10 centimeters, because that's the thickness of the insulation on both sides. So your characteristic length, to answer your question, is 3.28 meters.
Got it. Okay, thank you.
Okay, all right, so now we take a deep breath, and we've got most of the problem. We got most of the thermal resistances. We got that, and that, and that. Thomas, I think you're not muted. And now the question is, how do we get this? All right, so this is where we have to think about this, because this is going to be a little more challenging than the others, because we don't know this temperature right here. And the thermal resistance depends on the temperature of the body that's radiating, as well as the temperature of whatever's being radiated to. So this is where we have to use a bit of guess and check, or I like to say an iterative solution. This is exactly what a computer would do too. If a computer was solving this problem, it would use an iterative solution. There's no way to find this without making an assumption and then checking how valid was your assumption. So a computer can't do this either. A computer would need to do the same process that we're going to go through. It would just do it a little bit faster, obviously. So what can we do? Well, we're going to need R rad total. That's what this is. This is R rad total. So R rad total is equal to the surface and space resistance, which we can calculate. We have enough to calculate the surface and space resistance. We divide that by the Stefan-Boltzmann constant times the quantity T. I'm going to use subscript I for insulation here. So Ti squared plus T2, that's the walls squared, T2 squared, times the quantity Ti plus T2. All right, so we can calculate this, the surface and space resistance, but we're going to have to do something else for these. All right, so let's do that. The surface and space resistance, well, we've got a surface resistance at the surface of the insulation, the outside area of the boiler, that's the insulation. So we take 1 minus the emissivity of the insulation, which is given, divided by the area of the insulation times the emissivity of the insulation. That's the surface resistance of the insulation, plus the space resistance. That's 1 divided by the surface area of the insulation times the view factor from the insulation to the walls. And here, you have to use a little bit of intuition here. You have to say, all right, I'm ignoring the tops and bottoms of the wall and the boiler. So any radiation that is emitted from here, it's got to go in a straight line. They can't curve. So it's got to go out like this, or like this, or like this, or like this. Anywhere it comes out of this, it's going to at least make it to the walls. It's going to hit the walls. Whether or not it's absorbed by the walls is another question, but it's going to make it to the walls. So whenever a body is completely surrounded by another body, the view factor from body 1 to body 2 is 1. It's going to be 1. So you should be able to know that. You know, if you're given a problem, you won't get a problem exactly like this on the exam. I can guarantee that. This takes too long for me to give it to you on the exam. But if you're given a problem like this, then you definitely should know that the view factor here is 1. So that's going to be our F. And then we have a surface resistance at the walls, 1 minus the emissivity of the walls divided by the area of the walls. So that's the length times the height plus the width times the height, all of that times 2, because you got 4 walls. Divided by the area of the walls times the emissivity of the walls. So we plug in numbers for all of those, all of our emissivities, all of our areas of the boiler and of the walls, and you get a total surface plus space resistance of 0.03655, 1 divided by meters squared. So now we've got this, but we don't know what this is, the temperature of the insulation. We don't know what that is. So we're going to have to guess and check, like I mentioned on the video on Monday. We're going to have to guess and check. We're going to have to plug in a guess, and then we're going to have to check how valid was that guess. So take a wild guess at first. It doesn't matter how bad your guess is. I mean, it's better to be closer, I guess, but it doesn't really matter. So I'm going to first assume that the temperature of the insulation is 100 degrees Celsius. So if you felt the outside of that insulation of the boiler, it'd be 100 degrees Celsius. So that's what my first guess is going to be. It might be a bad guess, but that's what I'm going to guess. So now what we're going to do, we're going to complete basically all the problem with that assumption. And then we'll go back and we'll check with that assumption, what actually would the surface temperature of the insulation be? That's basically what we're doing here. So we're going to go back and we're going to check what is the surface temperature of the insulation, and we'll check what is the temperature difference between here and here, and we'll compare that to what we assumed with this. Because if we assume the insulation is 100 degrees Celsius and we know T of the walls, temperature 2 of the walls is 30 degrees Celsius, that means we're assuming a delta T from here to here of 70 degrees Celsius. So after we finish the problem with this assumption, we're going to go back and check what is this delta T. And if it's not 70 degrees, then we know that was a bad estimate. So that's the process we're going to do. So this is the same thing that I've got on the previous page. I just wrote it again. This is our surface plus space resistance. And this is our equation, Stefan Boltzmann constant times Ti squared plus T2 squared times the quantity Ti plus T2. Now I'm going to plug in values for the Stefan Boltzmann constant and for the insulation. So that's going to be 100 plus 273, which is going to be 373 Kelvin. That's what I'm going to plug in down here. So I'm going to plug in values for the insulation and of T2, the walls. But remember, it's got to be in Kelvin. It's got to be in Kelvin. So that's what I'm going to do. I'm going to plug in values here. Here's my assumption. The insulation is 100 degrees Celsius. So I'm assuming my delta T is 70 degrees Celsius because my 30 degrees Celsius wall temperature is given. So I plug in my assumed temperature for the insulation here and here. And then I solve this. I plug this into my calculator and I get our rad total of 0.00413 Kelvin per watt. And now I have an assumption for what our rad total was, but it's in parallel with the convection term. So I've got that convection resistance. I know that it is this, 0.0177 degrees Celsius per watt. So I got to put this in parallel with what I just calculated for our rad total. All right, that was right here. So that's what I'm doing right here. 1 over the combination of the convection and radiation resistance is equal to 1 divided by the convection resistance plus 1 divided by our rad total that we got from right here. So that gives me the resistance for the convection and radiation combined, which we can plug in here like this. So now my thermal resistance network, it was this, but now I just combined these two in parallel because they're in parallel. And now I simplified that to this. So now I can calculate the R total for this whole thing, and for this whole thing combined with our assumption for the temperature of the insulation, we get an R total of 0.11536 degrees Celsius per watt. So then I take that R total and I say, all right, that's my R total. And I know that the delta T across any of these resistances from here to here or from here to here, it's proportional to that individual resistance divided by the total resistance. This is kind of what I talked about in the video on Monday. We know that the delta T, the temperature drop across any of these resistances, is proportional to the resistance across each one divided by the total resistance. So that's what I'm going to do. Here is the delta. Here's the resistance for this resistance right here. So this is the resistance for the convection and radiation in parallel. That's this right here. And I'm taking that, a ratio of that to the total resistance that I got right there for the total. And then I'm taking that times the total delta T to tell me what's the delta T across here. That's what I'm trying to find. If it matches up with my assumption, then I'm good. If it doesn't, then it was a bad assumption. And I got to revise it. So that's what I'm doing here. And I find that my delta T with this assumption from here to here is 8 degrees Celsius. But my assumption was that this was 100 degrees Celsius, and I know this is 30 degrees Celsius. So my assumption was this delta T was 70. So 70 is not very close to 8. So it was not a very good guess. I did that on purpose because I wanted to make sure that I could do several iterations here. So it doesn't match our guess, so we got to try again. So our delta T was much lower than we had guessed. So we need to guess something lower than 100 degrees Celsius. So I'm going to guess that the insulation for this next iteration, I'm going to guess it's only 60 degrees Celsius. So that's 333 Kelvin. So that would make our delta T only 30 degrees Celsius. And now I can go back and I can plug into that same equation for R rad total. My surface and space resistances don't change. So that's fortunate. They don't change. The only thing that changes is this number right here and this number right here. This is the exact same thing that we had up here. The only thing difference is the temperature T sub I for the insulation. All right, so that's different and that's different. And that gives me my R rad total with my new assumption. And then just like before, I got to combine that in parallel with the convection resistance. The convection resistance doesn't change. We already got that. That doesn't change. So now this number is just a little bit different, which means that our combination of convection and radiation in parallel is a little bit different. So now it is 0.0039 degrees Celsius per watt. And now I can take that and I can calculate a new R total. I didn't draw the whole resistance network again, but I did calculate a new R total. And with that new R for the combination of convection and radiation, plus these resistances, I got a total resistance of now 0.11592 degrees Celsius per watt. And now, once again, I can find the delta T across just this one right here by taking the ratio of this resistance divided by the total resistance times the total delta T. So that's what I've done here. Here's the total resistance for the convection and radiation combined. Here's the total resistance for the whole problem. Take that times the total delta T, which is 270 degrees Celsius. And now I get that my delta T across here is only 9 degrees Celsius. So with this second guess, I had guessed the insulation was 60 degrees Celsius or 333 Kelvin, which would give me a delta T of 30 degrees Celsius across here and here. But when I went through the calculations, I found that actually with that assumption, the delta T was 9 degrees Celsius. So 30 degrees Celsius, delta T is not very close still to 9 degrees Celsius. So I'm going to do it one more time. I told you to make 3 guesses. So here's my third and final guess. And I'm going to be close enough here. And I'm going to guess, okay, the insulation at the outside of the insulation is 40 degrees Celsius, which is 313 Kelvin. And that would give me a delta T of only 10 degrees Celsius from here to here. That's my assumption. So now I go through that same process again. I calculate a new R rad total. The only thing different in here is this number for temperature of insulation and that number. And I find a new R rad total. It's 0.00551 Kelvin per watt. Then I combine that with the convection resistance again, and that hasn't changed still. And I find that the combination in parallel is 0.00420 degrees Celsius per watt. I calculate a new R total by combining with that and that and that, which haven't changed. And I get a new R total. And now I take a new ratio of the resistances. Here's the combination of convection radiation from there. I bring that to there. And my total resistance from there is here. And that's taken times my total delta T. Sorry, you couldn't see that. My total delta T. And now I get my actual delta T with this assumption is 10 degrees Celsius. So that's great because my assumption here was that my delta T across here was 10 degrees Celsius. And with that assumption, I did a calculation. And then I found out that with that calculation, my delta T across there was in fact 10 degrees Celsius. So it matches. It matches my initial assumption. So that's great. That's wonderful. That is the vast majority of the problem that finally we made it through. So we know finally what this temperature is. It's pretty darn close to 40 degrees Celsius, which gives us a delta T here of 10 degrees Celsius. Finally, okay, we got that. So with that, now we know all of these resistances now. So I just rewrote them. This is the same thing I've already calculated, but I just rewrote this resistance. This is for the convection and radiation in parallel. We already calculated that on the previous page. And we already calculated our R total also. It was 0.1162 degrees Celsius per watt. So that was the exact same thing that we got for our R total on the previous page. Now we just use that and we plug that into our heat transfer equation. Q dot equals the total delta T divided by the total resistance. Now it's easy. I just plug in T1, that's the temperature inside the boiler, minus T2, that's the temperature of the air in the walls that I'm transferring heat to. And there's my total resistance. And finally, I can plug this in and I get about 2,300 watts or about 2.3 kilowatts. All right, so that is how we do problem set 11. I know that can be a bit of a beast. I'm aware of that. All right, so I mean, you can probably use your judgment here, and you can say, look, how long did that take to review that? That took us almost 30 minutes or so to talk through that. When I was doing it on my own, it probably took me 20 or 25 minutes to do it, for me to do it. So I probably realistically, I can't give you a problem quite that complicated on the exam. All right. I can give you problems that use some of those same principles, but I can't give you a problem that's quite that complicated on the exam. So maybe that is some solace to you. I want you to understand that. Make sure you understand it. But there won't be a question that takes quite that much calculation on the exam. All right, so I'm going to stop the recording.